next talk on approximating equilibria in sequential auctions. This is joint work with Amy Greenwald. So over to you.
Yeah, I'm actually Victor, and I'm not an author on this paper, so I'm just the messenger, but feel free to shoot if you'd like. So this is work by my ex-advisor, Amy Greenwald, Jay Lee, and Eric Sadomka, and it's going to be about approximating equilibria in sequential auctions. So just to motivate the problem, auctions are ubiquitous, and a lot of money changes hands in auctions. So some examples are ad auctions or eBay auctions. And there is a lot of research going on trying to understand what the right bidding strategies are, what the equilibria are. So some of the research happens in simulated environments, like the trade and agent competition. So two examples at the top are ad auctions and supply chain management games. Then there is real industry search engine marketing, and there are flower auctions. There are different bidding sites. And the key challenges that a lot of bidders face is that well, first of all, it's game theoretic. So your optimal bids depends on bids of other agents. And in many cases, you have multiple auctions happening sequentially or simultaneously. And your preferences over items that are sold in those auctions may be combinatorial. But you have to bid in separate auctions. So, of course, there was a lot of work on auctions, both game theoretically and otherwise. So game theoretically, most of the results are for very stylized small problems. And there you would derive equilibrium, but it does not really apply easily to complex settings in the real world. Also, you could abstract away from complexity and say that we'll have a combinatorial auction, but then again, it does not correspond to reality. So to kind of bring closer together or to bridge this gap to at least some degree, what Amy has been doing for a while was, on the one hand, not searching for equilibrium, but not just Amy, a lot of people have been doing this, not searching for equilibrium, but assuming the environment is fixed and you're just optimizing with respect to the environment. So you assume that the bids of the other agents come from some distribution and you play optimal best response. So that's not going to be an equilibrium, but it may be a good bidding strategy. Then if you look at special cases or smaller instances of the same problems, you may be able to again apply some computational techniques, but then you could iterate and look for equilibrium. And you could try to use the lessons you learn from the simplified settings in the original, more complex problem. So today, well, I will focus on sequential auctions. Also, two examples of auctions that are more complex than usually have been tackled are simultaneous auctions. So that's when multiple items are sold at the same time. For example, items A, B, and C. And sequential auctions, where items are sold sequentially, one after another. And I'll run through a quick example. So we have 4 bidders and 2 items for sale, and we know that item B is sold after item A. So bidders have valuations. They have combinatorial valuations. If bidder 1 wins just item A, then his valuation is 10. Well, actually, he wants to win just one item, doesn't care which one, so his valuation is always 10. And bidder 3, on the other hand, prefers item A to item B, but if he wins both, there is some complementarity. So bidders, the auction for item A begins, bidders submit their bids, and let's assume that this is a standard auction, so the highest bidder wins. So bidder 3 is going to win. And let's assume it's a second price auction. So the winner is going to pay the second highest bid. So we give item A to bidder 3, and the second highest bid is the bid from bidder 1. So this is going to be the price that bidder 3 has to pay. So after this happens, and before the next auction begins, the information about the bidder, the winner, and the winning price is communicated to all of the agents. And so exactly what is communicated is dependent on the auction. But so in this work, it's assumed that it becomes known who won and what the winning price was. And then the auction for the next item occurs. And again, it follows the same rules. So there was a lot of work on sequential auctions in economics. And you could roughly categorize each work based on how many bidders, well, whether or not it handles more than 2 bidders, more than 2 rounds of bidding, whether the demand is multi-unit. So if it is a single unit demand, then each bidder wants just one item, and the evaluation is expressed by a single number. And whether or not it's incomplete information, meaning do you know the values of the other bidders? So in all auctions, you typically don't. And so none of this theoretical work handled the case where you have more than 2 bidders, more than 2 rounds, multi-unit demand, and incomplete information. There was also a lot of work in computer science. And well, there is the general purpose game solver Gambit. But when you talk about sequential games or extensive form games of incomplete information, the representation of the game is just enormous. So general purpose game solvers cannot handle it. There was also decision theoretic work where people express sequential auctions as an optimization problem. And well, as I mentioned earlier, try to find an optimal bidding strategy given the predictions about the behavior of the other bidders. And in this work, so this work does not just optimize with respect to predictions, it tries to find equilibria. And it builds upon the MDPs that were previously proposed. So I'll get into MDPs in a second, well, now actually. So the EFG, extensive form game, on the left is unwieldy. It's really enormous, and we're going to look not at the game, but at just one agent's point of view. So we'll optimize for one agent, and we'll encode his optimization problem as an MDP. And it's going to be what was termed a full history MDP, meaning that all of the information that has happened up to the current auction is going to be maintained in the state. So states will include the type of the agent and all of the observations that the agent received up to that point. And so there will be, each agent will have their own MDP. Well, actions are bids, and rewards will be assigned after the last auction. So then you can have fully combinatorial evaluations. And transition probabilities represent beliefs about opponents' strategies. So depending on what the other players bid, when you submit your bid, you may or may not win, depending on the distribution of their bids. And throughout, it's going to be assumed that values are independent. And then transition probabilities do not change, don't depend on the agent's type. We'll also assume symmetry, and we will focus on symmetric equilibria. So if you think about this predict and optimize approach, and an example of that is in a paper by Amy Greenwald from 2004, you are given, the optimizer or the agent is given, knows his type and predictions about bidding strategies of other agents. And so those predictions can be and encode transition probabilities of the MDP. Now, in this paper, in this work, we're going to ask where those predictions come from. And so we'll try to converge to an equilibrium, so to find predictions that are equilibrium predictions. So just a brief example. So let's assume that we know the strategy that everyone follows. Let's call it pi. And this is going to show how bidding strategies of other agents correspond to transition probabilities in the MDP. So suppose the strategy says that there are two types, high and low, and there are two actions, H, well, it's the other way around. There are two types, H and L, and there are two actions, high and low. And the prior is uniform, so you think that the other bidder can have type H or L with equal probability. But the strategy says that when the type is high, when the type is H, then the bid is high with probability 99%. And with 1%, the bid is low, and vice versa. So after you observe that an opponent won and the bid was high, then you use Bayes' rule to infer that his type is H with probability 99%. And so this updating is going to be a bottleneck, a computational bottleneck, and I will come back to it in a few slides, actually, now. So this, the transition probabilities, which we induce from the bidding strategy pi, consist, well, depend on auction rules, on the strategy itself, and on what we learn about opponent's type through the information that we receive. And the Bayesian updating is going to be complicated. So, but first, just a note that this encoding of the optimization problem as an MDP is actually correct in the sense that when everyone optimizes, and if they all find the same solutions, so if the solutions are consistent, then we have an equilibrium. So this is kind of the main contribution of the paper. It's this algorithmic procedure for looking for equilibrium in sequential auctions. And it's going to be an iterative best response type procedure. So you start from an arbitrary prediction about opponents' strategies. And so that from that you can infer transition probabilities. And then you you optimize. So you solve the MDP to get an optimal best response. And you can see how good this best response is. So how far it is from so if you play pi t, then when everyone else is playing pi t, so this is your kind of equilibrium utility, is if pi t were equilibrium, but it's not. So your best response to pi t is actually pi star. And when you calculate the difference between playing the same strategy as everyone else is playing and the best response to the strategy that everyone else is playing, you get the distance from equilibrium. And you keep doing this, and hopefully the distance is going to decrease, and you will converge.
So you say hopefully, presumably there's a guarantee, because it's about if there isn't any guarantee.
No, there isn't any guarantee. No. But well, experimentally it converges in the settings that were considered. So now we come to Bayesian updating, which is which is complicated. It requires reasoning about joint probability spaces of, joint distribution of opponents' types, and that gets computationally infeasible. So instead, we use Monte Carlo simulation. So we simulate the auction and record. So by simulating, I mean sampling values for the other agents. And simulating each auction, and then recording how many times the highest bid occurs. So record that in a distribution.
It's a sequential Monte Carlo.
So first you go through first auction, then you go to the second auction. So each sample is a pass.
Right. But you do it through time, propagating those individual paths? Or
I think in the experiment that were run, it did not matter because there were at most 3 rounds. And in the last round, you didn't need to predict much. You had a dominant strategy. But yeah, that's a good question. It could be the way. Yeah. So you build up those histograms, and then you use the histograms to do Bayesian updating. Okay, and so this is the same slide as before, but now we are just saying that instead of instead of doing real Bayesian updating, we are using histograms, and everything else is the same. So this was evaluated in 3 different auction domains, and those come from economics literature. And so there were 2-round and 3-round auctions. All was second price, and the number of bidders varied from 2 to 4. And the information that was revealed after each auction was the identity of the winner and the price. There were 2 types of tests. One followed exactly the model that was, one were for 2 rounds of bidding, and there are analytical results describing equilibrium in both settings. So the goal of those experiments was to see whether the equilibria remain stable. So if it's a strict equilibria, and in one case, it was found that, I'll get to that. And then the second set of experiments was for 3-round bidding, and there are no theoretical results for those settings, and the procedure converged, providing novel results there. So first, about the known analytical results. So 3 different models. Each graph is for a different model, and the interesting one is the middle one. In green, okay, so we're looking at strategies. What do you bid for each type? On the middle graph, so in green you see the analytical predictions, and in blue you see the best response, the strategy found by the procedure. So it was just one step of the procedure. That's why it's static and not iterative. And in the first and the third case, the lines correspond, indicating that the equilibrium is strict. In the middle one, the procedure actually found that there was a continuum of best responses, and then it was possible to derive analytically the lower bound of that region. That's the dashed line. And then focusing on the middle setting, they ran additional experiments, and the first graph shows the distance between policies in 2 consecutive rounds. And different lines correspond to different initializations for the beliefs about for the initial strategies of the other bidders. So the graph shows that the distance is very small, and the average utility was around 2. So in most cases the distance. Actually, sorry, that's for the last graph. The second graph shows that when you start, the bottom right graph shows that when you start from different initializations, you actually converge to the same strategy. So the distance between strategies that you recover when you start from different initializations is small. And the strategy that all of the simulations converge to is shown on a top right, and that's so because the bids were discretized, it's a step function, and that is the stable equilibrium, and it does not correspond to the analytical equilibria, well, to a particular analytical equilibria that was found previously. Then novel results for 3 rounds of bidding. So the graphs are, again, show that you converge pretty fast and that you converge to the same equilibrium, and the equilibrium is plotted at the top on the right. And again, you're pretty confident in the results. So the main contribution of this work is showing that this algorithmic procedure, well, proposing the procedure and validating it with some experiments. So you can find equilibria in sequential auctions using this best response dynamic, and you could approximate Bayesian updating using Monte Carlo sampling successfully. And so this resulted in some novel results, finding equilibria previously unknown. And then it helped analyze some of the known results. Well, and the results were pretty precise in terms of epsilon equilibria. So for future work, it would be interesting to explore alternative learning dynamics. So this could be, for example, easily adapted to fictitious play type of learning instead of just best response. Well, of course, it would be nice to scale up to larger games or try larger games. And maybe you would have to maintain a smaller state space. So it will become intractable to keep track of, to record full history in the MDP. And then you could ask questions like how the loss in information corresponds to the loss in utility. Thank you.
Great. It's time for questions.
Yeah.
What if the other agents don't update the policy in the same way as you do, when you still converge to the same equilibrium?
No. Well, so you don't really, this is self-play in a way. You're trying to find equilibrium. And so I think you're asking what happens. So we're not assuming that this is not a result that says everyone has to play the same strategy in the real world and then it all works. It's rather just a tool to find equilibrium. So if someone doesn't play their part of the equilibrium strategy, then it's not, it just means they're not playing equilibrium. But it has nothing to do with convergence.
But you still converge to something.
No, but so when you are converging, you're assuming everyone is playing the equilibrium. So you're assuming everyone plays the same strategy. Mm-hmm. So in the simulation, you cannot, no one has the option of not playing it.
Yeah, but what if the others are not playing?
Well, so if the others are not playing the same strategy, and if you know the strategy that they are playing, then you would just use decision theoretic approach where you view them as fixed opponents playing some fixed strategy and you choose your best response.
Yes, I mean, to follow up on that, presumably one can have equilibria where different people are playing different strategies.
Yeah, that would be non-symmetric, yeah.
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 So your MDP state space expands quite dramatically with the number of states that are considered. What size of problems have you dealt with in this sort of context? I mean, you gave a binary example there. I mean, how do things scale? How, when you're utilizing the Monte Carlo methods?
So I'm not the best person to ask, honestly,
Okay,
but so I only know about those experiments where you had 3 rounds of bidding, and you could discretize. Well, so the number of bids in this example is 10.
Right.
There are 10 steps. If you discretize values as well, I think you can go to also 10 or more.
Yeah. Okay. Are there any other questions? Great. Okay, well, thank you very much.